sit here.
Start or?
Yeah.
Okay.
Okay, get started. Eric, could you please close the door?
Yeah, okay. Good morning. Yeah, so today we are going to talk something about the OLED. So actually the OLED and LED, they're very similar if you see from the abbreviation. So one is LED and the other is OLED. So the O means the organic, so which means last week we talked about the LED. We said, oh, it's semiconductor. And OLED is the organic material. So looks like it's only difference. So I think the main purpose is we know what is organic, then that was done, right? So any idea about organic?
It's carbon-based.
Oh yeah, right. Oh, thank you, the teacher. Yeah, so it's carbon-based. Yeah, so it's carbon-based, and so for example, we can see a very big breakthrough in the OLED development. So let's see the organic material. What's that? First. So let's jump to the page 92 here. So that's really a big breakthrough in 1987 here. And it's by Professor Chin Tan. At that time, he was in Kodak. Right now, he moved to Rochester University. So that is the material they use. So you can see that is carbon-based. And you can see that's the phenol, something like that. So remember that typically for the chemical bond length, for example, here is a phenol over here, and here is CH3. So each bond is about maybe 1 angstrom to 2 angstrom, something like that, several angstrom. So you can calculate the whole molecule over here, maybe like nanometer range, several nanometer to 10 nanometers, something like that. So you can think about that. That is kind of similar to a quantum dot. So they can emit the light itself. So back to the semiconductor, we just described semiconductor last week. So how can we get the different band gap of the semiconductor? Because they have the repeated structure, right? So it's a buff. So it's a repeated structure, and we have the energy states, energy bands over here. So that is our valence band, and here's our conduction band. However, in the organic material, it's different. So for the organic material, typically it consists of the carbon, nitrogen, hydrogen, or oxygen, or something like that. But basically, it's a carbon-based material. So how can we tune? Remember that last week we talked about that. How can we tune the band gap level of the LED? How can we do that? We use different atoms. For example, we say, oh, we can use the phosphide system or nitride system for the long wavelengths or short wavelengths. So we use different atoms. So they have different bonding lengths, something like that, to attain different wavelengths emission. On the other hand, for the organic material, we always use organic. So they use carbon, nitrogen, oxygen, something like that. But we change their structure. And it's like a quantum dot. So that's a basic difference between the OLED and LED. So that is the we can see that that is a basic difference in emission. One is the bulk, so there's a lot of atoms. They have the for the LED, they have the very repeatedly connected to the a bulk system, and electron going transport in between these matrix. On the other hand, for the organic material, it's a molecule. So each is a molecule. So there is some difference in emission. They also have some difference in transport, because if that is an electron and transport in a single crystal semiconductor, so you can think about that when you transport in the LED. For example, it's a gallium arsenide. So 1 gallium with 4 arsenic. Something like that. And the electron will transport in some directions. So you need a single crystal. So we can find some directions, and you have some mobility, something like that. Okay? So it's a repeated structure. It's a framework, something like that. On the other hand, for the organic material, that is not a repeat structure. So you will think about it's a one molecule, the other molecule. Something like that. So if you put an electron over here, then how can you force them from one molecule to the other one? You have to put a very strong electric field so they can jump. Or typically we saw hopping. So hopping means you use your one leg to jump. So that's kind of very difficult to hop. So we also talk about, this time, about semiconductor. So what is semiconductor? So from the definition, the semiconductor means your conductivity is between conductor and insulator. Here. So right now we know everything already. So let's see, we can have the silicon, it's a semiconductor. We can have the gallium arsenide or many other different materials. So how about organic material? So actually, organic material is kind of insulator. So the conductivity is super low. So actually, it's very difficult. That's even less than the typical glass, less than your window glass. So your window glass is an insulator. So you cannot conduct your glass. You cannot put a current inside. So how could it happen to make your OLED to give light? That is very difficult. So actually, from the about 1950, 1960, and at that time, people think about, oh, we made possible we can do the OLED. So how about that? We just give the voltage to some organic material and observe the light. So what happened? They use a very high voltage, up to the 100 volt to 1000 volts, something like that. However, they will give light, and very fast, just a few seconds, something like that. So that is, I think, a professor who will talk about the liquid crystal display in the following weeks. So actually, there's a pioneer called Dr. Martin Schott. He's also the pioneer of the LCD. So one time we had the chance, maybe 8 years before, IDRC, yeah. So we had the chance to chat, and I told him, oh, my research topic right now is OLED. So the first thing he told me is, so how about the lifetime? So lifetime is always the biggest issue, most important issue for the OLED. So why we say that is organic? Back to the question, because that consists of carbon. But what is the the first definition of organic, because they say, oh, it comes to lives. So it's the organic, it's kind of the organ from the lives. So they have lifetime. Yeah, so at first time, that is very difficult to, you need a very high voltage to drive the OLED, and the lifetime is very short. So how to improve that? How to reduce the voltage? So from a very simple idea, voltage equals to current and resistivity, right? So why not we just reduce the resistivity? So how to reduce the resistivity? How do you think? How do you reduce the resistivity of a material? How can you do that?
Dopant?
Yeah, dopant. Yeah, it's a good idea. So dopant. Yeah, but unfortunately, it's very difficult to dope in the this kind of quantum dot. Because remember that for the LED, we can dope that because we can use something to replace that atom in the matrix. Yeah, we can dope some group 5 or group 3 material into your material, so they can provide the excess electron or hole. But it's not so easy. It's very difficult for the organic material. So the other way is we think about the resistivity is inversely proportional to the conductivity. So how about conductivity? It equals to NQ mu. And last time we write down here before, right? Last week. So if we have the dopant, we increase the carrier concentration. The other way is to increase the mobility, right? So they can move easier. So at that time, maybe 1970, so they tried to do some single crystal organic material. So they want to align the organic material so that maybe electron can find some channel, go through between the organic material. So that's good. So from the 1,000 volt maybe down to 100 volts or something like that. But that is not enough because right now we need less than 10 volts. So what's the other thinking about that? If we cannot have the very low conductivity, how can we reduce the resistivity? Equals to rho L over A, right? So we just made something very thin. So so it is possible to have the voltage reduced to some level we can accept. Okay. So actually, so the mobility value, for example, for the organic material, the maximum value is about maybe 1, or the best one maybe 10 or something like that, 20. For example, in this order. However, how about for the semiconductor? It's over 100 or 1,000. But for the typical, that is the crystalline organic semiconductor. But for the typical one, that is very low. That is the typical one we use right now for commercial. So you can see that's a quite difference, quite huge difference. So the breakthrough of the Professor Chun Tan is R2 two things. One is they use a very, very thin one. So you can see here, they use a two-layer structure. And each layer is about less than 100 nanometer. So you make it very, very, very thin. So you can have the low enough voltage to lead it up. Okay? So remember that as we said, talk about LED. We said LED, if that is a sapphire, then that's insulating. But for the gallium nitride, we need about 10 micrometer for the epitaxial growth. 10 micron. If you want to have the window layer from the side to improve the extraction efficiency, maybe you have to increase to the 50 micron, 100 micron, something like that. But for the OLED, it is not possible. Okay? However, there are other advantages for the OLED. For example, what's that? For the LED, that must be the single crystal. So we need the epitaxial growth. So we need a single crystal. So last time we said, oh, it's not easy to have the single crystal. We need some single crystal growth. So for the LED, they must fabricate on certain substrate. For the nitride, maybe the sapphire, or the gallium arsenide, gallium phosphide, silicon, whatever. That must be single crystal, because there must be a box system. On the other hand, for the OLED, that is different, because that is separate by different molecules. So this one is one molecule, the other is the other molecule. So typically, they are not so sensitive to the substrate. So we can have different kinds of substrate. So the single crystal substrate limits the size, because you need to grow the single crystal. So the size is limited. For example, 8-inch, 12-inch, or 16-inch, something like that. You cannot have the very large one. So remember, so think about that right now, or what's the size of your TV or of your laptop, something like that. So it's huge. So you cannot use this kind of the subject. You want to do something very large panel. So it's suitable for display. It's good. Okay, and we will discuss the second thing. That is they use a PN type. So right now it's difficult. We said, for the silicon, we can use the extrinsic semiconductor to improve the whole concentration or improve the electron concentration, so we can obtain the PN junction. However, for the organic material, it's not easy. Although it is something, in some cases it's possible, but not easy, to have the p-dopant and n-dopant. So we have to borrow the experience of the heterojunction. So we can use different materials. For here, for the diamine, is we call the hole transporting material. They have a higher mobility for the hole. So we play the game in the mobility for the material synthesis. So it's a hole transporting material, have higher mobility in hole. They have the higher electron mobility. That's the electron transporting material. So with two things, one is you have to reduce the thickness from micron to 100 nanometer range. So it is possible to lead down the device less than 10 volts. For example, here is the current density and the voltage. And you can see here, the turn on is around 3 volts. If you want to see the EL intensity, maybe 3.5 volts. So you can see the light emission, so less than 10 volts. So that is the basic difference. However, if you compare the device characteristics, last time we said there are something we need to something we can use to compare to illustrate LED. One thing is IV curve or JV curve, current density. So it's exponential increase. And for the luminance and current density is typically linear. And for spectrum, something like that. So it's an intensity versus wavelength. So it's the same for the OLED. So let's see what happened. So here is the semi-log. So actually they increase. So actually if that is linear, so increase quite rapid, but not exponential. Not so fast as this one. And we can you can see here if you see this curve, the current density, you can achieve maybe 8 volts to the 100 million per centimeter square. But if you go to the website, you can check for the LED. They can achieve this value, maybe much higher current density at 4 volts. So if you have the LED, you use the 3 volt and 4 volt, oh, that will be super bright because the current density is super high. That's exponential increase. So even though right now we have the very, very, very thin signals, still the resistivity is still higher than the LED. So the voltage of the OLED is still an issue, okay? Because the resistivity is still not so good. And you can see these two lines, basically it's parallel. So which means this one is valid. So the current density is basically linear to the current, but of course there are some other issues under the higher current density value. So how about the spectrum? So you can see here, for the organic material, typically they have a broader. So if we, in terms of full width and half maximum, so here maybe about 100 nanometers. So our we talk about a little bit about the color size. So we say, oh, we want the narrower band, right? Remember that? So we can have the better color saturation for the display application. For the LED, they can achieve we say less than 50 nanometer in principle. But for the OLED, actually it's a very broad band. The reason is, remember that is organic material. So actually there are some vibration or rotation. Basically it's vibration. So the vibration makes the emission band broader. So that is not so, actually the color saturation in terms of color is intrinsically not so good. But of course we can use some other method to improve that for the display application. However, on the other hand, because that is very broad, possibly it's a good option for the lighting intrinsically. Okay? So that is something we talk about the organic material. So so how do you think we can make some comparison between organic and LED? So because we are talking about OLED, so how about we say OLED? What's the advantage or disadvantage? How do you think? You can think about that. For example, for the compare with LED, VS LED. Pros and cons. How do you think? For the OLED, let me start it. So for the OLED, for example, there's a large size. Possible. Right? Because it was not limited by your substrate. So, what's others?
How about environmental impact? Is OLED less toxic materials involved? Is that correct? Is that a concern?
Yeah. Environmental
Impact.
friendly. Okay. Less impact. Yeah, there are lots of the issues. For example, as we said, if you want to have the epithelial growth, you have the arsine, phosphine, that's all toxic. And for the MOCVD epithelial growth or even the substrate, you need a higher temperature. For the single crystal, you need a temperature over 1000 degrees C. For the epithelial growth, typically it's about higher than 500 degrees C. On the other hand, for the organic material, no high temperature process because it cannot resist high temperature. So, true. Yeah. So you have to use the lower temperature process. So what else? So all good things, no bad things.
Fabrication more easily
Excuse me?
for OLED.
Uh-huh.
The fabrication is more easily for OLED. Is that right?
Compared to LED?
Yeah.
We can say that because for the LED, you need epithelial growth and you need device fabrication. But for the OLED, typically you just need have a good thin film, but you use an encapsulation as well. But on the other side is remember that the thickness is ultra thin. For example, 200 nanometer or so. So it's micrometer. So, do you have any idea what's the 200 nanometer? So your hair is about 100 micron. So that's 1,000 times less than your hair, the diameter of your hair. So that's ultra thin. And if you want to make, for example, the display, so that's 50 inch, very big, very huge. So how to make a very uniform thin film, that's very difficult. So possibly the whole process flow is shorter. You don't need many steps. But actually, that is very critical in fabrication, this kind of thin film. Okay, so we can say it's the shorter process flow. But the disadvantage may be the precise control. Something like that. Any other things you think about?
Color is more vivid.
Excuse me?
Color
It's more vivid.
is more vivid.
It is.
Which one?
LED. Yeah, typically LED is better. Yeah, so disadvantage. So it's also advantage and disadvantage. Disadvantage is the color saturation not so good. So which means the not for the display, maybe a bad thing, but that is maybe for the lighting. It's a good thing compared with LED. Of course, lifetime, right? And we will talk about some device characteristics here, and we will say the device time. There are two kinds of device lifetime. One is the operation lifetime. One is storage lifetime. Operation lifetime means if you operate this device, typically we use a constant current source. 10 million per centimeter square for the constant current, and you will see the luminance decrease with time. And the other thing is storage lifetime. If you store someplace here and use after 1 year or so, and you will saw there's a dark spot under the optical microscope. So we say that's the storage lifetime. So that is critical. So think about that. For example, actually the LCD, the liquid crystal material, they are actually also the organic material as well, but they use different function. For example, the OLED we want to use as a, looks like a semiconductor, so we want to have they can conduct the current and hole, and they can give the light. But for the LC material, they want to have some, they have some alignment, and they can have some optical birefringence, something like that. So what I want to say is, for example, for the storage lifetime, actually the organic material, basically we don't like to have water. We don't like water, so the water will degrade the OLED as well as the LCD. But actually, for the OLED material, for the OLED device, actually, the tolerance for water is about 100 to 1,000 more stricter than the LCD. So we have a term we call the WVPR. So that is the water vapor permeation rate. So for example, for the LCD and for the OLED, that should be less than the 10 to the power of -7, and this one up to the -4, something like that. Yeah, the number, I forgot, gram or centimeter square per day. Yeah, something like that. So that is very, very difficult for the OLED, not only the operation lifetime as well as the storage lifetime. You say, oh, maybe I don't use the display every day, so maybe the lifetime can be longer. Maybe not true, because you have to consider about the storage. Okay? So we talk about OLED and LED. That's thinner, as well as the higher drawing voltage, because the resistivity is higher.
What about the temperature effect on the lifetime?
Oh yeah, it's pretty bad.
Does that affect on storage, or probably both, right? Storage or operation? If we have an instrument in the car, now, although we don't operate, but this is so hot in Orlando. So.
Yeah, you are correct. Because, for example, the organic material, they cannot resist the high temperature. Yeah. So, yes.
That's basically exponential. We find in literature that's exponential.
Arrhenius law.
Yeah.
Yeah. That's true. So high temperature, high humidity aspect. So that's why for the display and lighting right now is not governed by OLED. Yeah, but they do have some unique features. They can. We want to solve this problem, right? So we say, oh, we can have the large size. So for the LED, that's a point source, and you need some optics to spray become uniform. But right now, OLED intrinsic is the planar source, so you can have the everywhere is kind of lighting. So it's possibly lifetime is possibly the lighting is a good thing. So you can see less environmental impact, shorter process flow. So that's their advantages. So that's the outline. We will have some introduction and show you some OLED display and lighting because why I'm here because I went to the SID conference and after that professor would say, oh, why not just sharing some LED and OLED here? So I will show you some pictures of something I took in the SID for the maybe 10 years or so. So there's a lot of interesting OLED display and lighting technology. And we will go to more fundamental part, is the optical, electrical characteristics of the organic material. So maybe because I will not go through every sections, but I will talk the most important parts. Then we will go to some advanced design. For example, the phosphorescent emission, that's a very important breakthrough in the OLED development. So I will use more time here. And tandem structure, it was used in some commercial products, and the white OLED is important. And tomorrow morning, right?
Yeah.
We'll talk something about light attraction. So if you are interested.
As a seminar, not a class.
Not a class, it's seminar. But anyway, I will record it. If you are interested, we can put it in the YouTube and you can see that. Yeah, actually, my student in Taiwan, they are watching the YouTube for these 2 weeks. Yeah, because I have the class in Taiwan as well. Okay, so it's a brief introduction. So as we said before, that's the typical OLED structure that was first invented by Professor Chin Tan. So that is because we don't need a special substrate, so we can use glass substrate, huge glass substrate, as large as 3 meter high or so. And we can use the anode and cathode material and sandwich the organic material. So some organic material, they can emit the light with red, blue, green, so we can achieve the display. So, but remember that's organic material. You just design the molecules and they can emit different kinds of color. Okay, so think about that. So last time we talked about the nitride system and phosphide system in LED, right? So right now for the LED, actually the lifetime is longer in the nitride system than the phosphide system, because we say for the nitride the atom is smaller, so the bonding strength is stronger. So how about the OLED? The lifetime. Actually it's reversed, because they use the same atom, carbon, nitrogen, oxygen, something like that. But if you want to emit the shorter wavelength light, which means a higher energy. So the higher energy, they will destroy the organic material by itself with some interaction. So that's the same. Why we say it's a kind of blue hazard. We say if your eye see the blue light too much, then that will affect your eye because that's organic. Okay, so it's reversed. Just we talked about the lifetime. However, so it's very simple structure. So we can have the anode, we can have the cathode, and remember that is super thin. So for the organic layer, maybe 100 millimeter, 200 millimeter, and for the cathode or anode, that's also the same. So that is thin in arbitrary substrate. So which means flexible is possible, right? So you can have a flexible display. And that's a very special, unique advantage of the OLED. So we can say flexible substrate. display. Right? So, but actually we see here is the organic layer, but actually it's not. So we say it's about 100, 100 or 200, but actually that is not only one layer. Actually there are lots of the many layers that have different functions, and we will describe these functions in the following classes. So, but anyway, one of the invention of the Professor Qin-Tan is use the PN junction to realize this kind of the OLED. So for the organic material, they still have the band gap, and the band gap determines the light emission colors. So the basic physics is we have the PN junction, and we have the anode, we have the cathode over here. So the first thing is we need to apply the voltage, then the carrier will go into the organic material. So hole will go from the anode, and the electron will go to from the cathode. And they, we say it's an injection and transport, and this kind of transport. You see here's a band. Actually it is not. There are lots of molecules. So from one hub to the other, then hub, something like that. So one important difference is the mobility. One important difference between the mobility of the LED and OLED is the for the semiconductor, typically mobility is insensitive to the electric field, normal condition. But for the organic material, the mobility actually is proportional to the electric field. Something like that. Increase sharply with the electric field, which means if you put higher electric field, they can move faster. Because you can think about that's kind of the quantum dot, and the electron want to go from this side to the other side. So it's kind of hopping. So you need a higher voltage, or higher electric field from one molecule jump to the other one. So that's the carrier transport. So then there are some heterojunction. So for example, they have injection over here. Then you can see there's a recombination. Because that is very small, like a quantum dot. So there are lots of quantum confinement effect. So they will form the acetone state. Typically for the semiconductor, the acetone states, if that is for bond material, it's not easy to observe. You have to reduce the temperature in semiconductor. But for the organic material, you have to view it as the size is like a quantum dot. So they have a very strong quantum confinement effect, so they will form the acetone. So here is a charge carrier for the hole and electron. Once they recombine the kind of acetone, then that becomes neutral. So they will not affected by the external electric field. So they will diffuse. So they diffuse for some times, for example, nanosecond, then they will recombine the kind of photon. So remember that, again, very, very thin, 100, 200 nanometer. So this thickness is comparable to the visible wavelengths. So there are some, you have to consider about the interference, that kind of thin interference. So there are lots of the cavity effect. So remember that here we use the reflective cathode, and here we use a transparent anode. But that is not always true. You can make this transparent and this one transparent, so that's a transparent display. But you cannot use both reflective, then light cannot go out. Okay. Okay, so there are lots of the interesting thing we can play. So let's see what we can do for this kind of the technology. Of course, the first thing is the unique thing is the flexible, right? So we can do the flexible display. So let's see. This demo is from the UDC. You can download from website. You can use a flexible substrate. It's a stainless steel substrate. So you can do everything you want on that. So that's long time before, so that was not very flexible. And you can see that very bad. Lots of the defects on top. So,
This is steel.
7 years.
At the UDC booth.
It's the same thing.
Same thing.
That's for the army. They can
But
put on their arms.
They had a demonstration of a backplane, thin sheet metal.
Yeah, that's
Is that in here?
substrate.
Is that in here or is that?
It's similar. So that's about the
But it's
same
on
thing.
this.
So that's the wearable 4-inch and QVGA full color. Flexible 80 matrix OLED is for the rock application. So it's fabricated on the stainless steel substrate. So for the army use, or something like that. And they can also, it's full color, but also they can fabricate infrared. So what's the purpose of infrared? Because during the night there is goggles to see the infrared, and they can see the image. So very interesting. So that's the UDC is a company for a lot of the OLED technology, especially for the materials. So they collaborate with LG. So LG is a very important panel makers. And that is also for the Sony. So you can see that's rollable. You can roll very small curvatures. And here they use the technology, not only the OLED itself. They use the transistor, they use the organic transistor, so all rollable. Sometimes the organic OLED itself is rollable or flexible, but the transistor is, if that is fabricated by the silicon, then that is not flexible. So here they use the organic transistor. So that is one example. And the other one is the by LG. How many years? Oh, long time before. So also the stainless steel. And very thin. So they hit the display. So the video shows that. Still alive. Very strong. Very thin. Yeah, but they have the sign, do not touch. Yeah, maybe they don't want somebody to do that. Yeah. Okay. So what else can we do? So we can have the ultra thin display, because right now the OLED itself is very thin, right? So less than it's about 1,000 times thinner than the radius of your hair. So we can fabricate on the very thin substrate. Then that will be very thin. So that is the display, and they call it flapping display. You can use the fan, and that is because that is very thin and very lightweight. So that's flapping. It was limited by your substrate thickness. Yeah, so you can see the display flapping. Oops. And you can have different kinds of the kinds of the form factor. So it's free form. So let me ask you a question. We said flat panel display. So what is the perfect shape of your display or your mobile phone? Or we should say, because right now there's a mobile phone, there's a pad. What is a perfect shape for your device? What do you think? We can write a pattern, right? So what should this device, what should it look like? Right now it's a mobile phone, something like that. And we want it thinner. We want this direction is thinner, right? And we want the display area is larger, but we also want to put in the pocket, right? So what's the shape? It should be.
It should be foldable, and if I put it in my pocket, because if it's soft, so it will not hurt myself.
Oh yeah, right. So it's kind of the foldable. Yeah, cool. So for the display, you should maximize the size when you use it. But for the display, you should be like the foldable umbrella. You can put it very small, something like that. Any others? Yeah, because in my university, it's a huge university. We have the different department. I'm in the ECS college. We have the medical school, and we also have something related to the bio. And they say the most natural shape for the human being. So you think from the human history. What kind of size can we take? He says something like the banana. So think about that. Why should we have a flat panel display? Possibly we can have something like banana shape or something like that. So we don't actually, sometimes we don't need we actually really need a flat panel display. So for example, right now it's you know your mobile phone is a machine, but why not? Because we have Siri right now, right? So we can talk with our mobile phone. Why not if we have a beautiful girl or a handsome boy like that, and you can talk with a beautiful girl, so every time you want to take it out to see that. So that would be free phone, something like that. So anyway, there are lots of the imagination or design, but anyway, OLED can provide this kind of this display. So they have the free phone, beautiful form factor. So actually, yes, that is true. They have some plan to move one by one. So that's last year. That is the Galaxy round. So they have some curve. So that is not flexible. Sorry, the fabrication that is bendable, or we should say that's still rock, but that's not a flat panel display. It's something like curve.
Yeah. Cool.
Yeah, something like round. And oh, sorry, that one was 2014. That was 15 and 16. So right now that's the age. So that is always for the next one. That will be the real flexible display. So that was from last year. It's another institute. SCL is a semiconductor energy lab in Japan. So they have this kind of the foldable OLED. So that is one display. And they have the flexible touch as well. So the touch panel is flexible. So you can use that when you want. See that. So when you open that, like a pad. When you close it, like a mobile phone, something like that. So that's really happening. So, but of course, that's just for demo. We are not quite sure how about for the real manufacturer. So that's the same.
Yeah, and close it, please.
Yeah, see? So that's one display.
Close it for
Yeah, here is about 3 centimeter of thickness. Yeah, not because of the OLED, because of the transistor. So actually, you can Google that in YouTube. You can find a stretchable OLED. So if that is OLED itself, that is not only flexible, that's stretchable. You can pull it out. So they can have the deformation about, I saw the video about 50%. So you can increase the size like that. So if you have flexible, then which means you can tile is seamless to become a wall. So that is also 2015. It's OLED. It's 81 inch, but that is a tiled display. You can see how bad it is. So that's one, something like that. But it's seamless. Of course, you can use an LCD, but there's a barrel in the middle. But if that is the flexible, then you can do something like that because you need some driving circuit, bonding area, terminal area here, so you can hide this area on the back. So that would be the seamless. So that is, but of course that's just some technology development, not yet to the mass production. Because so you can see when that is turning black, you can see that is not very good. However, that is just last week. It's also the tile. So that's 4 tile together. So let's try to see. Can you find the edge? Okay, let's see the video. Oops, no? Oh, sorry. Doesn't work? Huh. Not available, okay. Okay, but anyway, that is, they do some engineering work this year, and you cannot see that. You have to see very careful, otherwise you cannot see.
So this is 27 inch for each one, or this is total?
That is total 27. So that's the 13.5 panel. 13.5, yeah. And 4 panels tiled together. I mean, if this kind of tiling technology is established, then you can have no limitation in size.
Video wall.
Yeah, video wall. Yeah. So before we say, oh, OLED can be used only the small display, but if you can tile, that will be different. Okay, so that's for flexible. So any idea? So we can write a pattern. Okay, so let's move on to some other novel displays. So we can do some engineering works. For example, so here is a mirror over here. So this display actually you can see from this side and from the mirror. So it's a double side display. So it can be lit down and then from both sides, and you can see from one side when it was turned off, and that maybe it can be like a mirror, or it can be like a just a window. So it's kind of transparent display. And for this one, you can see here's also a mirror, then you can have the double side display. So from this side and from that side. Just two glasses. So very simple. Yeah, so this one was. And that's the dual OLED by Samsung. So you can do some engineering. So there's only one side emission, and that is
Transparency is
transparent.
40%, so if you turn off the image entirely, that's 40%.
So that's my hand.
Transparency, what it is, or the specification is with the black.
So you can use the transparent here, and you can see, oh, your ball is coming, so you can switch the windows like that.
Won't the contrast ratio be affected if the background, I mean the other side is bright?
Of course, yeah. So that's the application for laptop, because typically you use in the indoor. And if you use outdoor, that's easy to solve this problem by adding a cover or something like that. Yeah, but they just demo a possibility. You can use this kind of the transparent and useful for the laptop. And this year we will see later they make it as 55-inch, so it's kind of window show. And before it's a LCD window like that, and right now OLED can make similar thing. Yeah. It's kind of anyway. For the novel display here, I just want to say, oh, you can engineer in the electrodes, so you can let it's kind of the looks like the window, looks like the mirror, looks like something like that, and you can see from different sides. Yep. So what's that? So you can see here's the OLED display. And the car here is similar to your credit card. And it's fabricated on the stainless steel. So you lay down and turn it off, but there's no battery, right? No battery in our car. How does it work? So actually there's the RFID inside. So if you close to your sensor station here, and they can couple the electricity here and lead on your display. So they can do, so you can do something for the security things like that. So once you put here, then there's some information goes out. So that's my hand. So you cannot see anything. But if you put it close there, you can see. Yeah, so you can put some security information over there. And that is bendable. So even though I'm fat, that's fine. Okay, that's bendable. So it's a curve, but doesn't matter for your display. So that's Apple Watch. So you can. So actually, of course, right now Apple Watch that is rock, but actually the display that is bendable. So you can. They have lots of the interesting technology inside of the Apple Watch. And oops. Okay. It's another company. That's also the OLED watch. It's the AUO is a Taiwanese company, and they demonstrate similar product there. And you can also do some. Oh my. Oh.
You can use your own computer. Otherwise, you have to relink.
Oh.
Maybe just try to find it online.
Huh?
Is it available online, the video?
The video? No. Yeah,
No.
because I took that by myself.
Oh.
Yeah.
Bring your
Yeah.
laptop.
Yeah. Yeah, so I'm not quite, because that's the newest one, 2016. So, yeah. Okay, so let's see that later. We will have that. So, how about the larger size? Yes, possible. So I think that's 3-4 years before. 55-inch, and that's curved. So super thin. And they can even have the 3D, make a 3D display. You can see here some glasses. People over there to see the 3D display. And right now, yes, last year they have some, you can use the magnets put on the wall. So that's very, very lightweight. But super expensive, right? But you can see in the Amazon, it's much cheaper right now. Yeah. So, no, okay. So you can use not only the curve. So right now we said from the flat panel display, maybe you have some curve. Why we need some curve? We call that kind of immersive display. So you are in that kind of the, looks like you are in that scene. So for example, if you go to see the movie, if that's IMAX, that's kind of curved one. So it looks like you are immersion in that display. So that's kind of the 65 UHD concave. So you are inside. So when you play the game, you see, oh, there's the enemy. Boom, 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 something like that. Oh, thank you. Yeah, that's it. I need another connector
Do you have
in my backpack. Sorry.
backpack? Okay.
Yeah.
Wait,
Yeah, well-
do you use Apple, the iMac or PC?
Yeah, I'm Apple, sorry.
Oh,
Yeah. Sorry. So yeah, we will see that later. Then 55. I think this one should work because not this year. No. Come on. No. Okay. So actually, they have the 55, 65, 77 inch. Is the you can up to the close to 80.
yeah, I have a general question on the curved display. Yeah, it offers like immersive feeling, but only for one person, right? Only for one person who is sitting in the middle. But for TV, it's for like a group view.
Mm-hmm.
I would think it would make more sense if we have a curved, like a desktop computer, rather than TV.
Mm-hmm.
Because for TV, if you have more than one viewer, then only one enjoy the immersive view, but the others suffers. But for desktop computer, that's mainly for one person. So Do you think so, or you?
Yeah, because I went to, because I have kids, so we went to some play Disney or so. So there are lots of this kind of the immersive. They are huge display, and that's lots of viewers. But of course, the display must be very big. That can be cover all the people inside. Yeah, so I would say actually the curvature, yes, there are some effect. So maybe this is a trade-off. If 100 inch, maybe the curvature, thank you, maybe not so big. So, but for the laptop, yeah, sometimes it's too small to have this kind of immersive, or you can be very close. Yeah. So yeah, that's true. So possibly that's the reason for this kind of the concave.
We have to connect the.
I have the connector.
The projector connect the.
We have to.
Yeah.
Oh, that's fine.
Oh, I saw it.
You saw it? Oh, you are the expert.
Well, maybe. Maybe it's a reflection.
Yeah, it's very hard. It's very hard to see. I don't see it.
Yeah. Wait a minute, no, that's a reflection.
Yeah, very difficult, especially because if you want to see that easily, that's typically the dark scene. But during the dark scene, you cannot see
Right.
very easy. But of course, because they have some protect case in the front, so they reflect some light. So, yeah, but we can try again, okay? So it's 4. Tell you the solution first.
Yeah.
It's 4. 1, 2, 3, 4. So the line should be
Middle.
middle. Yeah, in the center. Okay.
Yeah, I saw the reflection, and reflection is worse than the division 9.
Yeah, you can see it.
Yeah,
You can't see it.
the reflection is huge.
Yeah, they use the reflection to cover that. You can say that.
You can't see it.
Yeah, it's good.
I mean, for steady image, it's easier to see the lines, but
Yeah.
for the dynamic, the moving one, it's harder.
Yeah, but I would say there's a huge progress from last year and to this year. So last year, they want to have a larger one, but you will see that very clear during the dark. You can see, oh, that's terrible. But this year is very beautiful. See, that's of the.
But But does the panel have to be like that? It looks so curvy. Does it have to be like that, or if we don't need it to be flexible?
Yeah, you don't have to be
Doesn't have
flexible.
to.
So you have some,
Stretch a little
Yeah.
bit.
yeah, or some flatten there. You put a glass, and then they will become flat.
And when you walk through the NBA building, there's a video wall there using the LCD. Then you can see the bezel, the black bezel, very easily.
Yeah.
Yeah,
and
but
the
this is much
airport-
thinner.
Yeah.
Yeah, it has to be within like a 3 pixel.
Yeah, it's definitely very interesting because it takes away the whole size constraint, so you don't have to worry about the size.
Yeah. So if the
You can
tiling
always
technology,
tile.
yeah, you can tile whatever you want.
But in terms of price, you know, which one is cheaper?
You are talking about.
Yeah, the price for the tiled and the single. You know, now you
Oh.
have to use like several
Yeah, right.
to
of course.
tile it together, right?
Yeah, if you
So
use.
for,
yeah.
for the tiling, you may need to have some special optics or stretchable edges to cover that.
Yeah,
So I don't know whether it really wins in the price or not. How much price difference between the single one and the like a full tiled together?
yeah, right. So talking about
Yeah.
for example, this one, you
Yeah.
can use a single one because right now we can have 55-inch. So how about this two?
I mean, I'm sure the 27-inch one will be cheaper, but they have to do something else rather than just put them together.
Yeah, I say it depends on the fabrication yield, something like that.
Mm.
Yeah. So the tile display must be very, very large. Yeah, you have.
I mean, for the video wall, then I understand, you know,
Yeah.
because it's beyond
Yeah.
like a Gen 10 size.
Yeah. But of course, for the smaller, it's kind of just demonstration of technology. I
Yeah.
don't think that would be the real products. For the
Yeah.
27-inch, you don't have to use the tile.
Right.
Okay.
Yeah. Let me show this one.
So that's actually the LCD, and under the very strong ambient light, and you can see that very clear. And the low power consumption. So the sunlight readability is super good. And driving mode, the power is only 0.1 milliwatt for the black and white display. But for the reflective display, like your paper or book, when there's no light, you cannot see because the luminance is very low. So they stack the OLED underneath the LCD. So right now they turn on the OLED. It's about 200 milliwatts. And that's cell emission, the light. So you can have the, they say the trans-reflective. You have the transmissive OLED on the bottom, and you have the reflective LCD on the top. So you have sunlight readability, you have very low power consumption under the sunlight of the LCD modes, and you can use the OLED when the room is very dark. But here they have only the reflective. The LCD is only the monocolor. So it is also possible to achieve the full color one. So that's the full color LCD, and it is a very strong light. But right now the power consumption is a little bit higher, 25 milliwatts. So when you turn off the light, it becomes dim. When you turn on the OLED, it becomes very beautiful. So OLED is about 200 yuan. So you can do lots of the different function. Use the OLED display to think about that. Many interesting idea. So that's what we saw. And that's the immersive display for only one people. So when you go in and you immersive inside into the game, you see, oh, to the right, to the left, and you will feel dizzy. So that's the just this year. So it's a 65 inch, and they have different size, 55, and they like use the dark background because OLED has a very unique advantage is their dark is really dark. So they have the 55, 65, 77 OLED TV. Yeah, but of course, very expensive. Super thin. Right now, they can hang on the wall, something like that. So that's 2 years before. So how about this year? So right now, they focus on the HDR. So that is a high dynamic range. So that's single display, that is not tile. And they like to use a little bit dark background, something like that, to demonstrate how good of the contrast ratio of the OLED. So Professor Wu will talk about LCD. LCD is kind of the light bulb, so it's control the light, go or block. But sometimes when you block it, you cannot block it completely. But for the OLED, it's the self-emission. So if you don't give the OLED a current, then they will just black. So they have the true black. So right now they focus on the high dynamic range. High dynamic range, so they can be very, very dark to the very, very bright. And typically the luminance typically is different for different kinds of the contents. For example, if you go to see the movie, they like to have this kind of the dark scene, and that's different from some TV shows. If you see the news, especially for the news, and that is very bright. So anyway, that's some different contents. But anyway, OLED can have the very high dynamic range. And they can use this kind of novel display for example, the transparent one. So it's kind of window show, and that is the OLED emission. So looks like the glass, but it's a display. It can be a display as well. Yeah, so 55 inch, and it's the same, similar one. This is another booth and focus on the anti-reflection, because if that is a transparent and if there's a reflection, and you will see the multiple reflection and the image blur. So this company has a very good anti-reflection coating. So it's just two glass. And you can see the image from both sides. But the luminance here is lower than this one. So they optimize in this direction. So you can have this kind of the transparent OLED as well as the dual view. So before, maybe 10 years before, the dual view is very small. And right now you can have the dual view and very thin from both sides. So that is the separate two TV.
Wow.
Yeah. So before our TV is hanging on the wall, something like that. Later we can put it in the middle. So both sides you can see. You can have different remote control to control the TV. So another interesting application is the virtual reality. There are lots of the companies, Oculus, HTC is a Taiwan company, or PS they collaborate with, I think with Sony or so. So they can have the very, very small display, and yeah, of course you can use LCD as well, but you need, because it's a hand mount, so you need a very thin, you need very compact. So OLED is a good choice for this kind of the virtual reality. So this year I think the OLED has some potential for this kind of the virtual reality. And as we know, for the virtual reality, that will be very, very close to eye because you put a glass or something like that. So you need a very high resolution. So this year is demonstrated also by ICL. It's 1058 ppi it's on the flexible substrate. So if that is for the eye, possibly that's curve is a better solution. The resolution is limited by my digital camera. That is very high resolution. And that is this year. And they have the very, very, very high resolution. It's also maybe 800 ppi or something like that. So higher than we say the retina display. We say the retina display is our retina can distinguish the pixel beyond this level. And they said last year that was not a virtual reality. They saw, oh, they have some research. So for example, why people can have 3D image? Why you can have the 3D perception? Why?
Because of 4 depth cues.
Because what? Sorry.
There are 4 depth cues. We call depth cues. What it makes us to perceive the 3D image. Can try to remember all of them.
Oh yeah.
You forgot already. Yeah.
Oh yeah, right. Let's.
Disparity,
Motion parallax.
motion parallax,
Accommodation.
accommodation.